All right. Hello, everyone. Can you hear me? Okay.
Yes.
Good. Thank you. Let's wait maybe a couple of minutes more to see if more people join. Now we can just start. Okay, just let's go ahead. So, good morning again. My name is Esteban Pedrueza, and I welcome you to this digital school on the Pilar Connect. I'll just share some screen. Can you see my screen?
Yes.
Yes.
Yes, it's there.
Yes.
Thank you.
Yes.
So, welcome to this digital school offered by INFRACHIP inside the Connect pillar, entitled Emergent Applications in Radio Frequency Technologies. This is hosted by Chalmers in the MC2 Department of Microtechnology and Nanoscience. So, before I talk a little bit about INFRACHIP, I would like first to thank you all the speakers for their kind participation in this digital school. I'm sure there will be very exciting talks today, and all the attendees that has come in today. So, what is INFRACHIP? I will go very fast about this. So, INFRACHIP's European-funded access that provides free access to state-of-the-art technologies. And bottom line, you can have your project done inside any of these partnerships that we have across Europe. So you may check all the details in our webpage, infrachip.eu. But basically, you can apply PhDs, researchers, postdoc, academics, and companies. You can apply remotely, meaning that the clean room or the partnership will do all the samples, fabrication, or measurements, wherever is the case, or in person by allowing the user to come to our facilities. How you can access this? You can apply and submit an inquiry, and then you need to describe a little bit in detail what is your project and what do you need the access. So after that, you will discuss with one TPOC, one technical point of contact of the facilities that you intend to use. And then an application is submitted, review it, and if approved, it can go immediately ahead. So I encourage you to subscribe to our newsletter and follow us in our LinkedIn page as well for news and next events. So I will just go quickly through the program today, and it's divided in two sessions. Session 1, we start with Dr. Zhenxing Wang for AMO. We will follow by Professor Aldo Jesorka from the company Go Motor. We will have a coffee break of 30 minutes after that, which I can also be available to answer some questions that you have. And then we will continue with the second session at 11 with Professor François Joint from Chalmers. And our last presentation will be done by Dr. Claude Leiner from Johanneum Research. So the maximum duration of the talk is 1 hour with 45 minutes for each speaker. And we have a maximum also of 15 minutes for question and answers. Please, when you have a question, just raise your hand. And when your question is answered, click again and raise your hand. So I can go through all of you. And if we have too many questions, I suggest you be very concise in your question and your answer. If there's no more questions, we can go and start the next talk. So I remind you, all of you, that all the webinars will be recorded and uploaded in all the INFRACHIP platforms for dissemination and education purposes. Especially we'll upload it, if you want to see it again, in YouTube channel of INFRACHIP. So I stop sharing now, and then it's my pleasure to present Dr. Zhenxing Wang from IMO, as I said, with a presentation titled 2D Materials-Based Electronics Towards Terahertz Range. So I leave now the floor to Dr. Zhenxing.
Thank you. Thank you for the introduction. I'm trying to share my screen. Center mode. Okay, is everything okay? Do you see also the full screen?
It's presenting very beautiful talk for me.
Yes.
Yes. Okay, great. Okay. Hello, everyone. So, good morning. It's rather early today, yeah? 8:30. So I'm Zhenxing Wang from AMO. So we are located in Aachen. So we are also partner in INFRACHIP. So today I'm going to talk about 2D materials-based electronics towards terahertz range. So this is outline of my presentation. So I will start with a little bit AMO introduction. And then I will talk why I was interested in 2D materials, and there were so many technical challenges, so I will talk about one of them, so electric contact, how to improve that. And then we move to high frequency, like radio frequency diodes and the one-dimensional metal insulated graphene diodes. So this then really goes to several hundred gigahertz operation. And then I will talk a little bit about the co-integration between graphene and transition metal dishulcanides. So in the end, I will talk about the scalability of the technology in general. So how can we make it on wafer scale? So yeah, so in the end, I will give a summary. So first, we'll talk a little bit about AMO, since AMO is also a partner in INFRACHIP, and we are also offering actually this kind of research access for customers or research institute. So I think it's beneficial to talk about it a little bit. So AMO is, as you can see from the map, we are located at the very west of Germany, so very close to, maybe I switch to the laser pointer so that you can see better. Yeah, so here, we are very close to also Belgium and also Netherlands. So actually, this is the building of AMO. We have a clean room of 400 square meter, and behind it, so actually this is like the triple point that so that really the three countries meet each other. We are, so the director of our institute is Professor Max Lemmer. So he also has a chair at the University of RWTH. So it means that we have very also close tie to the university. So this is one of the biggest technical university in Germany. Also, I think one of the best. And AMO has like 80 staff members, and at the university we have like 20 other colleagues. So in total we have like a team of 100 people. So we are really relying on research projects like European projects or national funding. Yeah. Also, it's worth to mention that we are actually a non-profit company. So yeah. And the technology that we're interested in, traditionally we're interested in silicon technology, and in the last, I think, 10 or 20 years, we gradually switch to new materials like graphene and other 2D materials, perovskites, plasmonic-based materials, so which has application in plasmonics. And the main application, it's electronics, photonics, and integrated sensors. Yeah, so switch to the next one. So this is our facility. So maybe this is helpful for the INFRACHIP proposal. You can see what we can do in the clean room. And I think one of them, it's not maybe here. So we also have a laser writer recently, or two even. So that's also something we can do. So different lithography, also pattern transfer, deposition, and also metrology. Yeah. So it's worth to mention that in-house we have a company called photonics. So they do terahertz conductivity measurement. They can do it over wafer scale. So they basically sell the tool. But yeah, so they also are interested in collaboration. So they can, for example, to see how uniform the graphene or other 2D materials on a wafer by doing terahertz conductivity measurement. This is impression from our clean room. As you can see, we're also partner of 2D pilot line of graphene flagship. So most of we can deal with wafers, as you can see, 6-inch wafers and also 8-inch wafers, and also we can deal with chips. I think in INFRACHIP so far what we get it's mainly on chips, yeah, since the cost is lower then. And in Aachen, we also have a center that has focused really on 2D materials. It means that we have a very good local network, even from physics all the way up to electronics. Yeah, so we have this multidisciplinary research center here in Aachen. Okay, so it's quite a lot about AMO then in our group. So our group is called the Graphene Electronics. So we are dealing with different 2D materials, and our main interest is mainly like different sensor devices or electronics device, optoelectronics devices, or high frequency electronics devices like you see here. I will show this actually in this presentation. We can also do everything, not everything, but most of the things we can also do it on flexible substrate, so that in the end we can realize like flexible sensors, flexible CMOS based on 2D materials and so on. So these are basically our main research interest. Of course, we have other groups like photonics. They're also involved in INFRACHIP. So I think then probably get idea what we can do. Yeah. Feel free to contact us if you have any request. Okay, now back to my presentation. Why are we interested in 2D materials? So as you can see, this is the scaling of the transistor, which is the base of the modern semiconductor industry in the last decades. Yeah. So as you can see, so this so-called Moore's law is still valid, but to some point, then it's not valid anymore because we are reaching, for example, a 5-nanometer node. Then we have to think about other solutions. One is to more and more. So as you can see here, so this can be actually realized. So it's basically to scale the material, scale the device further down. So this can be realized by other 2D materials like TMDs. So this is one of the focus also in 2D pilot line project that we are doing. And another option is to go above, then to go, we call it more than more, like to integrate photonic integrated circuit or neuromorphic computing circuit or quantum technology to the CMOS platform to add more functionality of this two CMOS. Yeah. And so of course, 2D materials can also be integrated like 3D on top of CMOS. So graphene has so many properties that are good for electronics, photonics, and so on. I would not go for it completely, but one of them I would like to mention is high carrier mobility, and of course high saturation velocity of carrier. These are the very important two factors that we are talking about today, because they are good for high frequency transistors. And also you can see that they are really suitable for flexible electronics. So at a point we can think maybe we can combine high frequency electronics and flexible electronics so that we can realize some system that you can wear to your body that you can also communicate with external environment. But for that, you also need some sensors that can detect like a body or to detect the environment. So for example, an infrared sensor could be interesting that you can see here with graphene, we can realize we can put quantum dots on top of graphene. So this is basically a diode. Yeah? It's titanium is electrode, and then we have a barrier layer. This light blue part is titanium oxide, and then we have graphene on top. This is a contact to graphene. So this is a diode, so-called MIG, metal insulated graphene diode. If we put quantum dots on top of that, then we realize a hybrid photodetector which can detect infrared range. So this, of course, is depending on also the size of the quantum dots. And also we can use graphene to realize a Hall sensor so that you can detect the magnetic field. And to be mentioned, graphene can also be used, or other 2D materials can also be used for temperature sensing, chemical sensing, and biosensor. Here, it's a pressure sensor that you put graphene on top of a cavity. Then when the pressure outside is changing, then this graphene is deformed either upwards and downwards so that you can detect the change of the pressure of the environment. So this we usually work with PTSE2. This is another 2D materials. So with all this, what I talked before, then we can think about maybe we can build a wearable system based on 2D materials for human body. So the main requirements are like self-powering. So this is important because we don't want to change the battery all the time. So maybe we can think of energy harvesting for 2D materials. That's also something we have been working on in another project. I will introduce a little bit about it. And another thing is a communication circuit based on 2D materials. Usually we require very high speed, so high frequency is also important. So that's the main topic today. And flexibility, this is apparent for 2D materials. And the scalability, I will talk in the very end, this wafer scale integration part. And then also the sensing functionality, graphene or other 2D materials really provides a lot of options, yeah, as I talked in the previous slides. So what we propose today is to use graphene-based technology to be more concrete, graphene-based diodes for communication circuit and server powering of such a system. To really make this technology useful, we have a lot of challenges to overcome. As you can see here, so the growth, transfer of 2D materials, interface, doping, contact, and design. So actually, ARMO, I think we deal with like the above 5. So design, I think we in 2DP we do a little bit, but it's not really our main business. So we do actually a lot in growth, transfer, interface, doping, and contact. But today, due to the time reasons, so I can only talk one of them. So I chose the one that we really put a lot of effort in. It's contact. How to improve the contact between the graphene and or 2D materials and metal. Yeah. So let's naturally switch to the next topic. So one of the technical challenges, electro contacts. So as you know, graphene has really small density of states near direct point. So this is actually the core why it's so difficult to inject carriers into graphene. That is also the reason why it makes the contact between graphene and metal so difficult. Yeah. So people put a lot of effort in it, like to use different metals and to use different thickness and to use different deposition technology, e-beam, evaporation, and so on. Also, the material can be from CVD or exfoliation or other materials from silicon carbide. And the measurement method also plays a role here. So in the end, you see basically all the values are available. So basically, there is no conclusive conclusions to say that one of the method is the best. So it's always depending on all these factors. Yeah, but we believe TLM is actually a good method to measure the contact resistance compared to other methods. So basically you make devices with different channel lengths, D1, D2, D3, and so on. Then afterwards you measure the resistance of all these devices, all these channels. Then you plot them in such a plot. So this is the total resistance you measured from such a structure, and this is the distance between the two electrodes. Then you plot them, and then you do a linear fitting, and then the intercept with the y-axis is actually 2 times contact resistance, because you have contact resistance on both sides. Yeah. So in the end, you divide this value by 2, then you get the contact resistance on one side. Of course, normally this also has to be normalized by width of the channel, because this also plays a role. The wider the channel, the smaller the contact resistance. But usually when you normalize it, then you can compare it. So there are also different methods to geometry to contact graphene, like you can contact from the top, from the bottom, or from the edge even. So of course we know edge contact delivers a lower contact resistance, as this is an example from more than 10 years ago, that they encapsulate graphene into 2 boron nitride layer, and then they contact graphene from the edge. Then they can really achieve like below 200 ohm micrometer contact resistance. I'm not sure if this is okay. This is not normalized. So here you can see that it's several hundred to 3 or 400 ohm micrometers. This is a really good value. So what we proposed in many years ago is to simplify this procedure. So this is our paper, that we try to first transfer the graphene on the substrate, and then we coat the graphene, and then we expose the area that we want to deposit the electrode, and then we etch the etch the graphene in this window. So then you achieve a cross section like this, and then you deposit metal directly here. Then you achieve actually an edge contact here directly. Afterwards, you do another spin coating, and then protect the channel, and then pattern the channel. So in the end, you get something like that. So this is a very easy approach to achieve edge contact. And you can see that we also achieve like 360 ohm micrometer or 190 ohm micrometer contact resistance. Of course, these are the two conditions. One is at the direct point, and this one is at the highly doped region. We confirm this contact resistance with KPFM, Kelvin probe force microscopy, to really measure this contact resistance, because you see there is really a potential drop at the interface which corresponds to the contact resistance. And then we also extract directly the contact resistance from here. Then we plot here is in the same range as the TOM method. So another approach is that we so-called holy contact. So we try to make a lot of holes in the graphene, so that to basically to increase the edge that you can inject the carriers. Then with that, we can really also achieve very nice contact resistance. So this is also what we have done several years ago. And another thing is that for doing this kind of holy structure, you usually use e-beam lithography, and you can see the diameter is like 100 nanometer. So it's very challenging also to do that. Also, it's very time consuming. Then we are thinking maybe there is a direct way, because you have to do a lithography, yeah, spin coating and so on, then exposure, and then development and etching. So we were thinking whether this is possible to also do it directly with laser irradiation, basically to break this graphene under the contact and then make the electrodes on it. This also we tried. I think this published last year. Then you can see this is a Raman map after the laser irradiation. Then you can see clearly this is, I think it's a D peak of the graphene here. Then you can see this area which is exposed with laser, it has very high D peak, which meaning that they're basically defective. Yeah. Then you can make contact on top of it. Then you can also do TOM and so on. We can also achieve very nice contact resistance. So of course, there is another material called MS2. It's even more difficult to make a good electric contact to these materials because of the Fermi level pinning and so on. So we were thinking maybe it's easier to make graphene because of this van der Waals stacking between the graphene and the MS2. Then, so we try to contact MOS2 with graphene, single layer graphene here, SLG, and then contact graphene with nickel. By doing that, indeed, we can also improve the contact resistance. It's rather low, you see. But of course, you see this star is our result from this work, and the triangle. We have still work that shows lower contact resistance here, but they're all from flake MOS2. So now not from CVD. Usually CVD, MOS2, they have worse quality, so that this also limits the contact resistance. So basically what we can achieve is really the best among all the scalable materials, meaning CVD materials. And this, I think this is our my last slide in this section, that we try to use plasma treatment for the area that we want to contact MOS2. Basically, you see this is a normal transistor that we contact directly with nickel, the metal. But this is what we propose. We sputter the area that we want to make the contact with argon plasma. So it's somehow also plasma treatment. But here we say that we have proof to show that this also actually modify the phase of this material so that it makes it more, so we form directly a heterojunction here, so that this phase, it's better for contacting. Yeah, it's a rather metallic phase. So that's what we call it, like a structural modification through sputtering. So this, we can also improve the contact resistance. So all have showed that you can see that so much can be done to just improve the contact resistance of between the metal and graphene or other 2D materials. Yeah. So there is still people are working on that to find the best solution to make the electrical contacts. Okay, so after we have a good electrical context, we can think about transistors, devices, yeah. We can think about transistors or diodes or different devices. We can make good devices out of it. So transistors, we work with transistors for some time, but after, especially for graphene, because it has very good frequency response, but since it has no band gap, it's difficult to make use of it. Then we were thinking, can we make something else with graphene? Then we were thinking about diodes. Everyone knows about diodes, yeah? So diodes, it's like if you drive a current through it, it can go forward, but it cannot go backward. Unless you apply very high voltage, then the diode is broken down, yeah? So it has a lot of applications for like radio demodulation, power conversion, and so on and so forth. Usually what we were talking about, it's high frequency diodes, sorry. That can work up to, let's say, several hundred gigahertz or even several, or even higher. Then traditionally people are using Schottky diodes or MIM diodes, metal insulator metal diodes, but it all has its drawbacks. So for Schottky diodes, it's not a thin film technology. It's based on graphene. It's based on silicon, so that you have to make everything on silicon, and so you cannot make it on arbitrary substrate. For the metal insulator metal diodes, it's thin film technology, meaning that you can do it on whatever substrate you want, but the frequency performance is not optimal because you see this is one electrode, second electrode, and there is a direct capacitance between these two electrodes, which then limits the RC, and then you have not very high frequency response. So what we propose here is graphene. I actually mentioned it before, metal insulated graphene diodes. So basically the titanium or aluminum, this is a metal, one electrode, and then you have titanium oxide here and graphene on top. And then you have the nickel contact to graphene. So then for this, we mentioned that this is a scalable process, since we also use ALD for the titanium oxide, and then we also use CVD graphene. Actually, the first work, I have to mention that this is not from us, it's from this work in 2016, but then we basically extend their work It's from Max Planck Institute in Stuttgart. So we extend this work to with using scalable materials. We prove that it has really good quality as well in 2017. Then so this is a performance, and we can see that in general this device has very good performance. This is our DC performance, so I will not go to details because of the time now. Then we also try to use this device for demodulation application, and you can see it can work directly up to 50 gigahertz without any further optimization. So this then it's the sensitivity is 1.1 volt per watt. So basically, the idea is we have an input with RF signal and output the DC voltage. Yeah, then this is what we measured. So with based on that, we even try to make an integrated circuit out of it, the so-called monolithic microwave integrated circuit. So we can integrate diode with capacitor, inductor, and resistor, and try. Then it opens a lot of possibilities. It's I have to say this is really a complicated process. It has in total 6 lithography layers and alignment and so on. So we did that time on chips. It's really a challenge, but in the end, I think we made it, and we were able to also demonstrate different circuits. We have published, I think, a lot of paper on this. So basically, we collaborate with RWTH Aachen University, circuit designer, and then they it can realize a lot of things. And some of them, they are like they can reach the state of the art CMOS technology. Some of them, they are even better than CMOS technology. So these are so as you can see here, the work are pretty old, but recently we are still working on that on a flexible substrate even. I will not go really into detail on that. So it's basically a K-band coupler based on flexible substrate. And the measurement is also, you can see that we put this flexible substrate onto a rod, and so it's curved surface, and then we can make the measurement with the GSD probes. Yeah, so then the next thing is I want to talk a little bit about the one-dimensional metal insulated graphene diode. So this is really an improvement of this kind of diode. As you see, as I mentioned before, that this 1D contact, we were thinking, can we really use it to build maybe a diode here on this interface? Then we really did it. So we add the titanium oxide on the sidewall, of course, by atomic layer deposition. So they can also deposit on the sidewall. And then the junction is actually here. The reason why we call it 1D is because the junction is actually a line here along this direction, along the X direction shown here. So it's really a line. So that's why we call it 1D diode. Compare this to 2D and 1D version, we can see the 1D really has much lower capacitive coupling because the junction is really thin. It's just a line. And we calculated the intrinsic RC cutoff frequency is 2.4 terahertz. But of course, this is really ideal. But at least I think we can demonstrate something which has higher frequency than 2D. Then we did it. This is a collaboration with Chalmers University, Jesorka, that we try to combine this diode together with antenna, the bow tie antenna, and then we shine the terahertz signal to the bow tie antenna. So of course there are some like terahertz beam and also silicon lens and so on. Then this antenna can absorb the signal and then to be rectified on the diode, and in end you can so the x-axis is the frequency and the y-axis.
Hello. Hello.
Sorry, I think I'm muted, right?
Okay, no, you are on mute now.
No, yeah, okay, sorry.
Sorry.
So
Let me ask if everyone can hear you now.
but did you hear something here, or
Yeah,
it's just okay?
Yeah,
Okay.
okay. I hear you now. Yes. Okay,
Okay.
sorry. Yeah.
Okay, sorry. Yes. Then we also use this. So later on, we also realized some other work using this structure. They use this 1D this graphene as a gate actually to control the MOS2 on the sidewall. So it's very similar to the structure, but this also works as an ultra-scaled transistor. So the gate is really 1 nanometer or even sub 1 nanometer because the graphene is very thin. Okay, so we have a project called Green Energy. So we try to use graphene technology. So Chalmers was the coordinator. The project ended already last year. We try to use this technology, graphene technology, to really make energy harvester. So the idea is to have a system that can self-power. So basically, we want to use the rectifier based on graphene here. So the idea here is to actually really rectify optical energy. We have some work up to several hundred gigahertz in the end that we prove that this kind of diode are still working. Yeah, but I could not show the result because we haven't published it, and since we are going to put everything online, so that I decided not to show it. But the work is on the way, and we show that this kind of diode based on graphene can work really towards. That's why we say towards terahertz, because I think it's 300 gigahertz that we have demonstrated. And another thing is that in another project called Whiplash, we try to develop graphene-based antenna. So I will try to really to be brief on that. That we have demonstrated graphene can work with and as antenna up to here you see 280 gigahertz. The advantage of graphene is that it's much smaller than the normal metal antenna for the same frequency range. And on another side, it's also tunable. So it means that you can tune the graphene by, for example, you can add a gate dielectric on it and then add another metal layer or another graphene layer on it. Then this layer can act as a gate. Then you can tune the graphene below. So then the oscillating frequency of this graphene will also be tuned so that you can have a tunable antenna. Yeah, so this is also very useful for real applications. So here we have demonstrated really the first ever experimental demonstration of graphene antenna with CVD materials. So in the end, the resonance is 250 gigahertz, so it's here. Yeah, and then this is metal and this is graphene, and the gain is minus 9.5 dB. So this is really also CMOS compatible because we can make everything on top of CMOS. Yeah, so then I will talk about a little bit about this co-integration of graphene with TMDs. So as actually I already mentioned many times that MOS2 is also another nice materials, 2D materials. Compared to graphene, it has advantage that it has a band gap. So for monolayer, it has 1.8 eV band gap. For bulk, it has 1.2 eV. It's also very good for flexible materials, for flexible electronics. So I want to show here, this is work from 2022, that we have demonstrated a MOS2 transistor that can work on flexible substrate, showing frequency response to several hundred megahertz. I know it's not good because of the mobility of the MOS2 is not good. It's only 1 square centimeter per volt second compared to graphene, several thousand of square centimeter per volt second. But people are still working on that to improve the mobility of such materials. And the good thing here is that I mentioned before that we can realize the power detector even with this several hundred megahertz frequency, cutoff frequency. And these are the benchmarking with other technologies. And the good thing I want to mention is that in the end, we can try to integrate graphene diode with this transistor. The advantage is that you can use diode you can, so the diode acts as an interface with higher frequency. Then you can convert it to lower frequency, but it has no band gap, so it's not a transistor. So you cannot do, a lot of work cannot be done. Then you can use further MOS2 transistor to deal with the lower frequency. Then you can make this co-integration. So this of course makes the whole thing more complicated. You have the inductor, capacitor, thin film resistor, and also MOS2 transistor and the MIG diode. So it's much more complicated process. But we also realized that on flexible substrate, and this was published in DRC 2 years ago, and now we are also writing a full paper on it since we also have some improvement in that circuit as well. Yeah, you see, really complicated circuit are realized. Yeah. Okay, so in the end, I want to say a few words about wafer scale integration of 2D materials. In the project called 2D experimental pilot line. So this was the previous phase of 2D pilot line. So we realized a multi-project wafer run here, that you see that we have designs from different customers. So but they share the same process flow. So we try to make this on the same wafer, and afterwards we dice them into small pieces and then ship them to customers. So this is actually very common in semiconductor industry for CMOS, but for graphene or 2D materials, this is actually the first trial that we have people have been doing. Then we also published a paper on Nature Communication this year, so to demonstrate the results from this run. Also this is the result from the wafer that you see the mobility. It still has a lot of variation on the wafer scale. Then also these are the specifications. So this paper actually is not about how good the performance are, but we really summarize this run and see how we also did some propose, not only from technical point of view, but also from like a practical point of how to deal with such a run, with to summarize our experience from such run, and then so since this really now we try in this 2D pilot project, we try to really scale this further up, and then in the end maybe we can run this through a Euro practice to really offer this as official run, and it should be then really reliable to customers. You can really promise the specifications. Yeah. So this is the 2D pilot project that we're running now from last year. And in this project, we also have different runs scheduled, for example, for AMO, VTT, IHP in Germany, and Graphinia. So IMEC, in the end, they may also provide a TMD run, but it's still open. Yeah, because they have more focus and on TMDs, and they also have also larger scale, like 300 millimeter wafer. And okay, so in the end, I want to give a summary of my talk. So basically, what I want to say for the whole talk is that graphene and TMDs are suitable for RF and flexible electronics. There are so many technical challenges to realize in the end, to realize realize high frequency, high performance devices, but we just talk a lot about contact resistance, because this is really the basic that we want to realize, and we put a lot of effort in the last years. And here I demonstrate also the metal insulator graphene diode. It performs very well at high frequency. So without any optimization, it can already demonstrate frequency response up to 50 gigahertz. And also we realize a lot of circuit. It's called this integrated circuit based on 2D materials. And then we were thinking some optimization with this one-dimensional variation, and then it shows frequency. Then the rectangle shows response up to 170 gigahertz. So in the end, we also showed how we can co-integrate TMDs with graphene, and how to make the advantage of both. One is high frequency response, another one has a band gap which can work as a transistor, which can be switched off during operation. And in the end, we also demonstrated wafer scale integration is possible and with 2D materials. So graphene, I think, is somehow mature in this project. And then in this project, we're also trying to realize TMD-based wafer scale fabrication. That's all from my side. So there are so many projects that we have run in the last years with this topic. So I list all of them here, and I have to acknowledge my AMO team here on the right-hand side, and also the ELD team. So basically the chair of the university. So we really is one team, and of course, thank you for your attention.
Okay, I would like to thank Dr. Zhenxing Wang for his nice presentation. So I would like to open the floor for questions. So just raise your hand, please. We have one across the chat. It says, hello, Zhenxing. Could you comment on the current methods for RC optimization, such as achieving clean contact semi-metals and van der Waals contacts? Which one is the most promising in your opinion? I don't know if you can see one, Zhenxing, the comment. Yeah.
Yes, I can see the comment. This is actually a colleague from Aachen as well. Gleb, thank you for the question. Yeah, so for the semi-metal, actually, we because we have a lot of I mean regulations in the clean room, so it's not easy to introduce new materials. So we don't have too much experience in semi-metal. I have to admit that. So we want to try something, but it's always difficult. Yeah. So, but from I mean, from literature point of view, I believe the semi-metal method is more promising. But that's only my personal impression from this from the literature that I've seen from before. So I think it's really worth some trial in that direction. Yeah. So we wanted to try something all the time in the past, but yeah. Now I actually have to mention that from November we have a new project called 2D Addict. Then we really try to address these kind of challenges together with I think we have University of Milano there, Polytechnic University of Milano, so Roman Sorten there. So we really try to realize scaled transistor, and of course then there, I think it's a possibility for us to further explore such approach, for example, semi-metals, yeah. And also IMEC is also involved in the project. So it's that 2D Addict project, it's more about individual transistors and how to really further optimize the performance. Yeah. So it's not about scalability, not really, but high performance. Yeah. So sorry, that's only what I can answer now. You are muted.
Sorry, I'm muted.
Yeah.
So I think it's Berma Satish who has a question now, please. Unmute yourself. Yeah.
Hi. Thank you for very nice presentation. It was quite informative. I was wondering, do you have any application, I mean, implemented application for the MEMS sensor or NEMS sensor, and how challenging it is to make 2D devices as a mechanical point of view? I mean, how face you if you have implemented something? Yeah, thank you.
I can maybe show the MEMS. Yeah. I guess I should go back to my slides. Okay, it's, I think in the beginning rather. Yeah, so I think we have some, sorry. So here, yeah. So what we have worked, actually this is rather activity in the university. So in this, so we collaborate with them in the chair of Max in the university. So what we have been doing so far is basically this pressure sensor that I mentioned, that you seal the cavity with 2D materials. Then when the pressure changes, then you can detect it from the measured resistance. So the main challenge here is that the scalability of this process. So to make one device which is working is of course easy, but if you want to make this wafer scale, and always if there is a hole in this region, then it's done. Then you don't have any. Then the device is dead. Yeah, it's not working anymore. So I think in this work 2024 that my colleague Sebastian Lucas, so he demonstrated really how it's possible to scale this process to wafer scale. So there is demonstration. It's not perfect, but you can see, I think the yield is already very high there. And then I think it was either last year or this year, it's also ACS Nano paper, if I remember correctly. So they demonstrated the integration of this kind of MEMS devices with CMOS. So we really put the CMOS below, and then on top of that, they built this cavity and then the MEMS device, so that the sensor is on top, and then below you have the signal processing with CMOS. So this kind of integration, it's also demonstrated there, but I think I missed to put it there. So the name of my colleague is called Sebastian Lucas. If you see this paper, you can find more information on that. So he has another paper on the co-integration of this kind of sensor. So yeah, that's the technical challenge. I think it's more important. Yeah, so that really to make it this scalable. Yeah, but in principle it works pretty well. Another thing to mention that with graphene usually it doesn't work really well. So they use PTSC2 because it has larger gauge factor, meaning that with the same change of the structure with the same deformation, you have more resistance change, so that it's more sensitive then. Yeah, so that's why PTSC2 is really the best. I think in this paper from 2020, this is really a benchmarking paper of all this. It's a review paper in this field. Yeah, so they really benchmark different materials as well. Yeah.
Thank you.
Thank you.
Yeah, I can see the paper. Looks very interesting. Thank you.
Yeah.
Okay. More questions, please? I think I will have one on my own. What do you think it could? Do you have any information about what are the industry requirements on the contacts? Let's say the electronics or semiconductor industry, they're looking for specific parameters to be under some threshold.
I think I see your point. I don't think they have a threshold value that they say, okay, it has to be below the value. Usually it's the lower, the better. Yeah. Also, of course, for some applications, actually it's not too important. For example, the diode that I've shown here, it's if I go to this slide. Yes, now I share my screen. Share my whole screen. So for this diode, actually, you can see this metal graphene contact is not too important because the total resistance is actually dominated by this junction, this barrier layer. So so it's always a relative thing. So in this case, I would say you don't have to really go for perfect contact. If it's like a 1 kilo ohm micrometer, I think this is already very good. So usually I think so roughly we say if the contact resistance is 1 kilo ohm per micrometer, then we say that's already a good value. If you can go below, that's extremely good. So it's like a 500 ohm micrometer and so on. So I mean, that's what I can say. Yeah. So from not compared to semiconductor to silicon or CMOS industry,
Yes.
but rather in the field of 2D materials, I would say 1 kilo ohm micrometer is a good value. Yeah.
Okay, thank you very much. Any more questions? Maybe we have time for one question more. No? Okay, then just introduce now to our next speaker. So our next speaker is Professor Aldo Jesorka from the company GoMod, and he will present his talk titled Surface Acoustic Resonance in RF MEMS, Principles, Design, and Applications in Liquid Phase Sensing. And he will also will have a first look at the next hands-on training that we'll have here at Chalmers for the next year. So I suggest that you stay tuned, as I said in my introduction, with all the INFRACHIP communication apps like the website and the LinkedIn page. So can you hear me, Professor Jesorka? You're muted.
Yes, everything is fine. Okay.
Yes. Thank
Wonderful.
you for coming today.
It was a very nice talk about the 2D materials, and we are moving on to a subject that is not too far away. It's also a sensor-related subject, but the MEMS connection is very clear, but the materials are pretty different. So let me just start my presentation. So you should be able to see the presentation now.
Yes, we can see it.
That's correct. Okay, then I'm interested in surface acoustic resonance in RF MEMS, and I will specifically talk about the in liquid sensing in a microfluidic setting. I'm Aldo Jesorka. I'm a developer at GoMod and co-founder of GoMod AB, a company in Sweden that is dedicated to STEM education. And we are a small company that is building interactive miniaturized instruments in order to bring technological.
Aldo, I think that you're freeze. Hello.
On training.
Hello.
Is one of.
Sorry, I think that you were freeze for a second there, like 10 seconds or something like that.
Okay, that's not good.
I think you are good now.
Yeah. Okay. I'll continue. Just to repeat this briefly. So we are building interactive miniaturized instruments of technological processes that includes all STEM fields, chemistry, physics, engineering, and also clean room processes. Hands-on education is our main concept. We want people to actually experience in a screen-free environment the technological processes that dominate our technological life industry. And we are bringing this in the form of modular instrument simulators, but we also do hands-on training in an actual cleanroom environment. I myself have for over 20 years worked in cleanrooms on all sorts of projects, mainly including life sciences. That means sensor development, surfaces for biointerfaces, and so on. So here's an example of one of those instrument sets. It's located within the chip technology field. So we are building small modules of different components of clean room processes. Here you see a low pressure CVD instrument. There's a control module, a plasma chamber for deposition, a gas supply, and the pump, and it's suitable to be put on the desktop. It doesn't use any chemicals, it doesn't use vacuum or anything, but it allows you to simulate the entire process, including all parameters, and that is integrated into the CMOS process. Here is an example of a 2 micrometer CMOS chip production process, and with 10 modules that can be combined, you can go through the entire process, the 13-step or 13 major step process, to basically learn how CMOS technology works and what instruments you use, what parameters you use in order to understand the deep foundation of the technology. So today I'm talking about an area in which I've been working for a long time, at least a decade. I used to be a group leader at Chalmers, where Esteban is currently organizing INFRACHIP, and I was working in integrative micro and nanosciences, and that included also the application of microelectromechanical systems or MEMS systems in life sciences, especially for sensing. So today in this webinar, I want to give you an overview over the concepts that are there about the concept of surface acoustic wave devices, MEMS and SAW sensors, the concept of surface acoustic resonance, what it brings us in comparison to other devices of that type. Then I talk about the microfluidics integration, little introduction, and summarize. So what you can get out of this webinar is conceptual knowledge. I will not go into details, but I will give you at the end some literature references and people that are very knowledgeable if you really need to develop chip devices in the life sciences that are based on MEMS, then these are the right people to help you to design and bring your idea into the clean room. And we at GoMod are also dedicated to sort of making bridges between technology researchers and people that have a need in interdisciplinary interaction. We understand this field very well, and we are very happy to sort of help building these bridges and making projects successful. So quick introduction into MEMS, micro-scale electromechanical systems in the micrometer to millimeter range. And what's important here is that a mechanical motion is involved. On the micro scale, flexible elements are involved. And the fabrication of these MEMS devices, of these mechanical devices, is using clean room technology, lithography, etching, deposition, etc. And here on the left, you see one of those classic pictures from Sandina. It shows you the scale by having captured that mite on top of a chip. But what is most interesting for us is a little gear work that is in the lower left corner that represents mechanical devices that have been microfabricated on typical clean room materials, in this case silicon. So what are the benefits here? Miniaturization, of course, things are smaller, and small is not a benefit in the sense of nice to have. It is an actual necessity, and the reason is lightweightness, high integration, low power consumption, and the necessary high performance and precision and actuation. So fast response times, which also scales with size, and especially the high mechanical stability. The resonance frequencies of small structures are much higher than for larger structures, which makes it much more complicated to sort of bring these structures into resonance and makes them disintegrate. So cost-effective production, batch fabrication is possible. Everything you people know from your own work, but batch fabrication is always wanted. Wafer scale processes, semiconductor compatible processes, where you can use the tools and procedures that are used in semiconductor fabrication. So, and then what's also very interesting is the integration capability. You can combine sensors, actuators, all kinds of different mechanical tools and combine them with electronics on a single chip. And if this is desired and certain compatibility rules are matched, then it can also be combined with fluidics, and you can use it in, for example, in vitro diagnostics and other life science diagnostics applications. So a few examples are mentioned here in the end. You know, on the right hand side, there's a little drawing of a motion sensor that is very typical in cell phones. There's a lot of MEMS integration in cell phones, not just that, also the filters in the high frequency range. So these sensing devices, these sensing devices in cell phone applications are commonplace today. A bit more exotic is the Chalmers micro pinball game. Unfortunately, I don't have a nice picture of it, but I've seen it in the Chalmers clean room. It's actually exhibited there in the entrance, and that was an relatively complex educational implementation of MEMS to show its capabilities. And everybody knows, of course, projectors and the micro mirror arrays in these projectors are also MEMS devices that are actuated electrostatically to actuate pixels in an image, and that has to happen also at reasonably high speed. So, and sub-branch and subfield of MEMS are the so-called radio frequency MEMS, or radio frequency electromechanical systems. These are miniaturized devices that combine the electrical and mechanical components to control RF signals. And in the previous talk, we have already seen that there's a need for this. There is, of course, a large market for all kinds of RF devices, including cell phones and wireless internet. So the functions of these devices is to switch signals inside a cell phone, for example, to tune over a frequency range, or to filter radio signals in communication systems. And with filtering, what we mean is to select a frequency band in order to use it for exclusive transmission of signals in that band, and blind out everything that does not belong to that signal that is outside that band range. So key components are switches, variable capacitors, resonators, and filters. And resonators and filters are particularly interesting here. There's a very large market. All cell phones contain a large number of filters for different application, different frequency ranges within that signal processing in the phone. Wireless communication, 5G, nowadays 6G at higher frequencies. I'll come to that in a second. Radar system, satellite and defense electronics. So what are the characteristics of RF MEMS? What types of motions and actuations can be achieved there? Electrostatic actuation uses electrostatic forces between charged electrodes to create motions. I just mentioned the DLP, the little mirrors that are electrostatically moved. There's thermal actuation, somewhat rare, but it uses the thermal expansion of materials when heated, and it's Joule heating. That means for larger displacements at low voltages. And third is piezoelectric materials, which has the smallest displacement and also very peculiar properties. And specific materials are used here, piezoelectric materials. When exposed to an electrical voltage, electrical field, they are changing the interaction between, they're changing the distances between the atoms in the crystal grids, and get relatively small actuations, but that are often sufficient to serve the purpose, as in filters, for example. So advantages of such RF components are low insertion loss. That means when you bring a signal into this device, not much energy is lost in that process. A very good insulation. That means the frequency band is very well separated from everything that is not belonging to it. Power consumption is low. Linearity is very good, and that means if you have a certain frequency range that you want to transmit within that range, all frequencies are equally with equal characteristics moved through this MEMS device without distortions at the upper or lower end of that frequency range. And then clean room processes can be applied, and that is really something that everybody is interested in, and we have also learned about it in the previous webinar, that clean room compatibility and wafer scale fabrication is really what is wanted, and RF MEMS are excellent applications for clean room processes. The challenges in RF MEMS are mainly the materials and packaging. Packaging, because an RF MEMS device works very nice in air, but when you package it, the package is influencing its characteristics, and therefore sometimes ruining the parameters. So the packaging has to be from the very beginning included into the design and the development. So for 6G, which is a new era that is coming up, that is a sub-terahertz band that goes from 100 to 300 gigahertz. It is full of challenges, parasitics, losses, thermal challenges, miniaturization, speed, and packaging. And it has advantages over conventional RF devices, especially in that high frequency range. The reconfigurability, we learned about tunable antennas as an additional example of why reconfigurability is important. So if you have a tunable antenna, you also want to tune your devices, your filters, etc., to sort of match the frequency of the antenna. These two things are interconnected. Linearity and low loss for the signal when it passes through the device. 6G is, of course, an frequency band that gives a lot of opportunities, or produces a lot of opportunities for new devices, tunable filters, reconfigurable antennas, we already learned about it, and also very high quality resonators that give an excellent transmission of signal. So the performance metrics of such devices are the insertion loss, how much energy is lost while passing through the device, the Q factor, what is the quality of the resonator. Q factor, to illustrate what it means, is if you're having a bell, a church bell, for example, and you're ringing it, you're hitting it, and you're ringing it. So the Q factor is equivalent to how long does this bell actually ring before the frequencies or the vibration is dampened until it no longer exists. And then, of course, switching speed and reliability. Filters have to work 24/7 in a cell phone device for many years, and the industry expects high reliability in this area. So that brings us to the next topic, and these are the surface acoustic waves. So surface acoustic waves are mechanical waves propagate along the surface of an elastic material, of a piezoelectric material, and the amplitude of this wave, because it's a surface wave, it decays exponentially with depth. So that means few micrometers from the surface, the signal intensity is low. So it's essentially the surface that is important for the communication of signals through the device. These surface acoustic wave devices are widely used in sensors for signal processing and in telecommunications. The key features of SAW are they are confined to the surfaces of the material. The wavelengths are in the radio frequency range, micrometer to millimeter range, but it can also have much lower frequencies, and they are in the megahertz range. They are sensitive to surface conditions, particular stress, mass loading, the presence of certain molecules. That is what makes these surface acoustic wave applications interesting in sensing. There are a few types of surface acoustic waves. Most important are the ones on the left, the Rayleigh waves and the Love waves. The Rayleigh wave is kind of interesting. It is in the direction of the field, but it's perpendicular to the surface, and it has an ellipsoidal motion of the atoms in the crystal structure. So you can see this if this is your transmission direction. So it's a motion like this. It goes out of the surface. It's above the surface. The second case here, the Love waves, are waves that are in the plane of the surface. They're not getting very much out of the surface into the bulk above it. And then there are higher order waves that are typically also relevant in film themes. These are the Jesorka waves, and they typically occur in layered structures, and they're very interesting for high frequency applications because they are faster than the other types of waves. Okay. Now, something that some of you might have already asked yourself, RF MEMS and SAW, is that the same? Do they actually belong together? Is it a borderline case? And the answer is yes, it's a matter of definition. If you strictly go by MEMS definition, RF MEMS are microfabricated electromechanical devices that have free moving parts, such as cantilevers, beams, gears, and so on. So they must have free moving parts that are disconnected from the rest of the device. While SAW that are also MEMS, of course, they are microfabricated, they are RF capable to very high frequencies, and they are electromechanical. And some people distinguish and say, okay, MEMS have to have discrete mechanical motions, and SAW is propagating acoustic waves where the mechanical motion is material intrinsic. I personally see this as compatible. I think like this distinction makes sense as a definition, but I would still consider SAW devices as a subgroup of RF MEMS. Both exploit mechanical motion for electrical signal control, and that is what matters for me, and is probably also what matters for the developers. The RF MEMS are reconfigurable electronically, and SAW uses acoustic waves for filtering and sensing. They use a shared technology framework in terms of production and packaging. So let's look a little bit into surface acoustic wave devices. We take the two examples from here, the waves that go into the bulk and the ones that are in the plane, and look how they can be applied and what the differences are. How do you actually bring electrical signals into the piezoelectric material? There are piezoelectric substrates, materials, which we will talk about in the next slide. These substrates have to be addressed. The electrical energy has to get into the piezoelectric material and out again. And that's a transduction principle, and that transduction is achieved with interdigital electrodes. as can be seen here in the middle of this slide. And we're basically applying a high frequency signal. Go through these to the fingers of an IDT, which is actually producing a mechanical motions, and these waves are passing in a SAW device through a second IDT in which it is picked up and can be used, for example, in the next stage in a cell phone, if this is a filter device. What is interesting here, it has a relatively narrow frequency range in which this works. So if you're designing the electrodes with aperture, the distance here between the two horizontal beams and the pitch and the way they are arranged, then you can get a very nice transduction property, a very nice way in which the signal is exclusively moved between the IDTs, while everything that's outside the resonance frequency is strongly suppressed. And here's a side view of this. For a transducer of that type, it's not really that important what type of wave it is. The end-lauf waves work very well. It becomes then interesting when you want to have microfluidic, if you want to use your IDT device in a liquid medium. We'll get to that a little later. So what we see is essentially it's transduction principle. You are bringing energy into a piezoelectric device, and it comes out, and on the way back, it's reflected. On the way back, it interacts with the desired phenomenon, and comes out, and you can read out the changes in the output channel. There are different ways of how to do that. Before we get into this, let's talk about the surface acoustic wave device materials. So there are bulk piezoelectric materials. Quartz is very common. Some of you might be familiar with the quartz crystal microbalance, which is also a MEMS device, which works at a much lower frequency, below 10 megahertz, and it's very commonly used in life science laboratories to determine the interaction of molecules with surfaces. It's very common nowadays are lithium tantalate and lithium niobate. They have very good electromechanical coupling. That means you can get the electrical energy very nicely in and out of the piezoelectric material. Tantalate is somewhat better than niobate in terms of thermal stability, so that temperature changes, small temperature changes, have no influence on the performance of the device. Modern materials that are also useful for higher frequencies are aluminum nitride and scandium-doped scandium aluminum nitride, which are with a very much enhanced piezoelectric response. And aluminum nitride with a wide bandgap and high SAW velocity. So these bulk piezoelectric materials have been used for quite some time and developed into commercial filters and so on. And lately, a new technology has emerged, and these are the layered or thin film substrate, and that is essentially a small layer of an piezoelectric material that is deposited on an insulator or a silicon wafer. And what one can say about this is, first of all, typical niobate tantalate wafers are extremely expensive, and these, and especially the materials, are expensive to get. So one is trying to get to shoot several birds with the same stones. On one hand, use less of the piezoelectric material, at the same time make the performance better. And these very thin layers have an excellent temperature characteristics, and they also enable high frequency, low loss devices. There is a problem with aluminum nitride and also scandium doped aluminum nitride that is not air stable. So they are, when exposed to water and oxygen, they get oxidized and form aluminum oxide. So that means the material degrades relatively rapidly. They have to be packaged in a proper way. But aluminum nitride and scandium aluminum nitride are, especially on thin layers and thin film substrates, are what is currently mostly being researched. And the choice of material affects frequency and efficiency, and also, as I said, the temperature stability. The layered substrates make things higher, better performing, and miniaturization is enhanced, and especially in filter applications. So if you want to make SAW devices, that means you have to get IDEs on piezoelectric substrates, be it iobate wafers or tantalate wafers, or also other thin film devices. So the typical fabrication process is comparatively simple. It is not the fabrication itself which is a challenge in this field, but it is actually the quality of the materials that are deposited. So everything has a strong influence on the device performance. Here in these 9 points is what you typically get to bring a SAW device in a shape where it is applicable in microfluidics, which we will also discuss a little later. But let's quickly go through this. Substrate preparation: polished lithium niobate wafer. Lithium niobate is a transparent material. If it is very pure, it has a slightly brown color. There are also very dark ones, and that are not as pure. And they are typically cut in a certain crystal plane in order to select what type of waves are propagated through the material. So you start with a photoresist and photolithography steps, so photoresist coating, baking, etc. Then comes exposure, either through a mask or with a laser writer and development, and you already have your IDEs defined. Then you deposit the electrode material, could be gold, aluminium. Then comes a lift-off and etch or etching. You remove the excess metal to form the electrodes, and it's not just the electrodes. The contact pads are also typically connected to this. You are then do an annealing and final processing step, optional thermal treatment, and if you want to use a liquid environment around the sensors, you are putting an insulating layer on top of the IDE, so they are not short-circuited in the medium. That is typically several micrometers of silicon oxide. Micrometers is ideal because also of the temperature compensation, but it's typically very disliked in the clean room to deposit that large amount of silicon oxide. So with 100 to 200 nanometers, you can already get pretty good performance. So then device completion, you inspect the electrode integrity, you see if they have a resonant in air, and then you can dice, contact, and integrate in whatever device you want to use. So for sensing applications, there are two types of devices. Classic ones are the surface acoustic wave devices. There's a graphic explanation here. So you are essentially inserting a signal that passes as mechanical waves through the device, and it's read out. It's a so-called two-port device. And what you're interested in is how are the waves, as they are passing through the device, how are they influenced by the molecules or the agents that you want to sense. And the sensing is based in this case on changes in the wave propagation. That means the velocity and the amplitude as the signal passes from the input to the output port. And this input-output port device is one configuration. There are also others, but that is the most common one that we have also investigated in our lab. So it's very useful to detect pressure, temperature, gas concentration, and some biochemical species. It has a fast response and is also suitable for inline sensing. And in the previous talk, we have already seen that this type of device in combination with graphene has not lost any of its appeal. Quite the opposite. People are kind of driving it in the direction of new combinations of materials with piezoelectric materials. So in contrast to the SAW devices of that type, is something that comes out of my lab. We have patented in 2018, I think, the so-called surface acoustic resonance concept in liquid sensing. And the surface acoustic resonator is kind of interesting because what you're doing is you are inserting a signal into a device, for example, here in the IDT, and it is basically then being reflected back and forth between two reflectors that are on the opposite side of the IDT. So if the propagation of the waves is in this direction, so the signal is basically resonating, you're creating standing waves, and the energy is stored. So here's an equivalence circuit. It's essentially an oscillator. And what you're then looking at is how does a sensing molecule, a molecule of interest, influence the shift in the resonance frequency or the length by which this thing keeps its energy, or in other words, the Q factor. And it has very high sensitivity to mass loading, temperature, and pressure changes. Mass loading is very much wanted. Temperature is not so much wanted. That's why in this particular area, these new layered materials with temperature compensation are of great interest. In any case, it's a new concept where actually energy is stored within the device. And what you're getting out is a number of parameters that makes this device actually a multi-parametric sensing device. Mass loading and actually the Q factor, both of these factors can be independently evaluated. So at the bottom here, I actually also show a few implementations of sensing devices, how this is being done. So on the left side is the classic piezoelectric device, which is also implemented in the quartz crystal microbalance. It's a quartz slice that has electrodes on top of bottom, and there's a shear motion in this way. And when you're putting molecules on the surface of these electrodes, then the motion becomes slower, and you can evaluate this change in frequency versus the amount of material that has been deposited, thus the name quartz crystal microbalance. And the other two cases are sort of very interesting, in particular for sensing, but not only. On the right side, here under C, you see the devices that I've just been describing. You have finger electrodes, interdigital electrodes on top of piezoelectric substrates. That is for those waves, that is snake waves that are moving in the plane of the surface. And for the other ones, there's another option to do that. You have a thin film device with electrodes on top here. And these devices are most interesting in the filter development, especially in the 6G band. If you're going in very high frequencies, then the IDTs don't work very much anymore. And one of the reasons is that the pitch of the electrodes becomes so small in the nanometer range that they cannot be reasonably produced anymore. Also, the performance drops accordingly. While with this principle that is shown here in B, the resonance frequency is decided by the distance between the electrons. That means the layer thickness. And here, once again, the material quality, the way, for example, scandium aluminum nitride is produced to form these thin layers or even freestanding membranes is one of those magic things that everybody is working on in order to get better performing devices here. So we have now an idea of what SAW devices are, what kinds of devices there are, and now comes our practical application. That means the implementation of SAW sensors, of these acoustic sensors, into microfluidic applications. So acoustic waves can be used not only for sensing, but also for the manipulation of droplets and fluids. Biosensing and manipulation have about an equal share. I would say that sensing is somewhat more interesting, but both of them have at the moment an equal share. Well, the challenges in this field are the damping that happens when the waves, when the resonators or structures are brought in contact with liquid, then the packaging, the implementation of the microfluidic channels, the materials, and the thermal stability. You can imagine that you're having applications with liquids. That means they can be a little bit warmer, a little bit colder, you know, depending on where they were flowing past, if somebody was touching it, and so on. So it's slightly different from filters that are stably put into a cell phone. Possible solutions are hybrid materials, these layered materials that we talked about, and also potentially AI signal analysis or other sophisticated ways of sort of looking at signals and extracting information there. Something that is worthwhile mentioning is that these RF devices can be irradiated with radio frequencies, and that allows a powering of the devices, and at the same time it allows wireless readout. Was also hinted by the previous speaker that this is of interest. The SAW sensor acts as a passive resonator, and you are bringing an RF signal in there, which starts the process of transducing the signal through the piezoelectric material, and at the same time you can read out the reflected signal, the back reflected signal, and compare it to the signal that you have presented to the device, and the difference should contain your sensing information. Again, there's no power needed, battery-free operation, and it is very reliable in extreme conditions, no cables, no contacts. It also has a fabrication benefit. So it's therefore suitable for remote and for real-time sensing. So microfluidics itself, I have a little slide here to present it to those who are not familiar with the concept as such. Microfluidic systems means low Reynolds number systems. The Reynolds number is a dimensionless number derived from the Navier-Stokes equation, which cannot be currently fully solved. So one has to go other ways to for simulations, for example. But what it brings out is several dimensionless numbers. One of them, there's the Reynolds number, which is actually the ratio between the moment of inertia and the viscous forces. And you can see these as two opposite forces. The inertia means if you're bringing something in motion, you're applying pressure and you're making fluids move, and it has inertia, it wants to continue move, but at the same time there are viscous forces, there's drag, and it kind of slows down this entire movement. The Reynolds number is here. Density of the fluid, of course, goes on the flow velocity, the characteristic length scale, and also the viscosity of the fluid. And when we are talking about microfluidic systems, we are talking about systems of low Reynolds numbers. That means the moment of inertia, or the inertia, is of minor importance. It can be neglected, essentially. So the entire system is ruled by viscous forces and can be completely controlled by applying pressure to the fluids and making it move. pressure gradients. Beginning and the end of a fluidic channel, for example, has a pressure gradient, and that drives the fluid to the channel. What you get is what you see here in this little picture. You have basically 1, 2, 3, 4, 5 channels that are next to each other. Every other channel is labeled with a fluorescent dye, like fluorescein, for example, and then they are pushed out with the same pressure. And you can see that the fluids are coexisting. The streams are coexisting. They're not turbulences. They're not mixing. They only start mixing at longer length scales because of the diffusion of the molecules across the borders of these individual streams. So what does it mean? It gives a high degree of reproducibility. It makes sure that sample ingredients contents is being delivered from one end of the chip to the other. Mixing is only by diffusion. That is sometimes a benefit, and in other cases it is a disadvantage. If you want to mix systems, you have to make an extra effort. And surface acoustic wave devices, especially the Rayleigh waves, have the ability to actually instigate these mixing motions by the formation of vertices, for example. So, and if we remember what we have seen first, the Rayleigh waves, the one that have an elliptical movement in the direction of the field, but out of the plane, then you can imagine it works in contact with water like a little peristaltic, like a little peristaltic pump. It basically moves the water. The wave moves the water in the direction of the field, along the propagation direction, and that means it is very inefficient for liquid measurements because that motion causes a strong energy loss. On the other hand, if we have sheer horizontal waves that are in the plane, that are not penetrating much into the liquid, you still get dampening, but it is not as bad as with the Rayleigh waves. So you have minimal energy leaks into the liquid. You have to take care that you also have by design, little energy leak into the bulk material. If that is being taken care of, you can get excellent, very sensitive sensing devices for liquid viscosity, for density, for thin films on liquid surfaces. If you, for example, functionalize the surface, you can detect the attachment of antigenes to antibodies or similar. So here are device implementations from our own lab. I have to bring for the first time up here Kirill Kostanovic, who was my PhD student for 4 years until 2019. And he developed the surface acoustic resonance chip and implemented this with microfluidics. What you see here is the interdigital electrode here with a resonator with the IDEs in the middle, and you have just bars left and right that are reflecting the energy that is being coupled into the IDEs. And on top of that is a PDMS piece. It's a silicon rubber that can be used for imprinting channel structures, and it's bonded here. And what you see now here is that the signal has a air cavity on top of it so that it's not damped, and then it transfers the energy that comes here in the center into the IDE, and it's being then back and forth reflected, and the sample is sitting here on top of these reflector electrodes. So the energy that is stored here is basically being probed. Signal goes in and signal goes out, and while there's sample in these chambers, it has an influence on the propagation of the waves back and forth between the reflectors. Here on the right side, you see what is happening when you are looking at the resonance. Here in this case, 185 megahertz approximately. When you go from air, that is the black curve with a resonance frequency, and to water, millicube water, which is the red curve, you see that there's a frequency shift, and nicely that also some of the extra resonance disappear here. in broken lines, you see that the phases of the signals, the zero crossing here of the phases can also be used as an indicator of presence of molecules, change in viscosity, or similar. There's a relatively large shift, 900 ppm, and that is at least one order of magnitude larger than what one would expect from temperature variations. So it's a robust system that is very useful here. So we also made a reference design that is the classic two-port SAW system. You have a reflector with an IDT, and there's a fluidic system that is placed over the part of the SAW device through which the wave propagate, and it is actually in port B received and then analyzed. If you compare these two devices and you see this one-port design, this resonance design is much simpler in terms of requirements. You have only one port. That means the electronic the need for external hardware to read out and implement the system is much reduced. So which problems do we solve? First of all, microfluidic chips are used extensively nowadays in life science assays. We replace bulky benchtop systems, the one that I've found here. This is not from our own lab. The one on the right one is from my own lab, but this one is not. I don't remember exactly where I got this picture, probably with a collaborator. We were taking this picture, but it illustrates very well the difference between these two concepts. One is very bulky with lots of tubes, with lots of lines that is transferring samples, large pumps, etc. While in a microfluidic chip here, this blue part is a PDMS chip, a relatively large one, I have to say, several centimeters. Yet the assay processor is internally, of course, more sophisticated, but in terms of materials, in terms of size, of energy consumption, and so on, of course, superior to this type of device. And when it comes to performance, they're at least equal, if not better. So what we also have here is a fully automated system that is resource saving, and the chip itself is a consumable, which is kind of nicer and more resource friendly than having lots of these tubes and probably using many dozens in experiment. So the summary: MEMS, the foundation of many different types of microsystems in different areas of technology nowadays. RF MEMS are adaptive, reconfigurable, high-frequency electronics that are predominantly used in communications, internet, Wi-Fi, and mobile telephones. There we have made a transition from 5G to 6G with new challenges, which could be addressed by a combination of new device concepts with new materials. There are surface acoustic wave devices that one can see or may not see as a subcategory of RF MEMS. They are also used for acoustic signal processing, but also for sensing. If you combine surface acoustic wave devices with microfluidics, you get smart lab-on-a-chip devices that have numerous benefits, including wireless readout options, and a special variant of these surface acoustic wave devices are the surface acoustic resonance devices, which actually store the energy, and you have the ability to create multi-parametric readout, and which gives you special benefits in the analysis of sensor or sensing molecules. So that is the end of my talk. I want to mention the good people that were with me in this development process of the MEMS devices that I've shown you. And there's Dr. Wenceslav Janchev, one of the world experts leading experts in design of SAW devices, particularly filters, and Kirill Kostanovic, the PhD student who worked with me for 4 years, who was engineer in filter development in Huawei, and is now has his own company. And in combination with that, a good read to which I would like to point you is Kyril's thesis, The Integration of Surface Acoustic Waves and Microfluidic Technologies for In-Liquid Sensing. Mentioning that, I will also tell you what I haven't talked about today, and that is a lot of theory, design tools and processes, the process details in the clean room, and details on the sensors and the optimization process and measurement and automation on the sensors and with the sensors. And many of these things you find in Kyril's thesis. And with that, I end, and I'm looking forward to questions and discussion.
Okay, so thank you very much to Professor Jesorka for this very nice presentation. So I open the floor for questions. Please go ahead and raise your hand. Maybe start with maybe one question that I have is what do you think are the current challenges for applying MEMS in the industry, if you regard to the microfluidics, especially?
It is actually a relatively small community there. There are very few companies that are actually making these devices, and the biggest challenge is the material. To get the right crystal structures in these thin layers. And the next challenge is the packaging, because if you are bringing these devices into a solid environment, it changes the characteristics significantly. So this design process, which is simulation and modeling in combination with some empirical testing of different strategies, that is a real big deal at the moment.
Good, thank you. It's basically because there is any other alternative that is more cheaper, that maybe is not as good, but maybe.
No, I mean, what I can say is, if you're looking at wafer scale production, everybody wants wafer scale production. Yes. The current chips are really very, very tiny. They are just like a square millimeter or so, and you have thousands of chips per wafer. That means that the prices for these devices, if you can bring them on the wafer scale, are really very favorable.
Okay.
And but it is definitely a challenge to sort of get them onto the wafer, especially since, for example, for lithium niobate or lithium tantalate, there are no 8-inch wafers. I think 6 inches is the biggest size that you can have. So that limits, of course, the upscaling here. And that is something that I think the field has learned to live with. But since you can get so many hundreds and thousands of devices onto a wafer, it's not really a very big problem at the moment. But the prices per chip, after dicing, is relatively low in the mid-range cent region.
Okay, good. More questions? If there is no more questions, maybe Professor Jesorka, maybe you can introduce a little bit about the hands-on course that we will have next year at Chalmers.
In the talk that the process to make these MEMS devices is relatively straightforward. And since we are not using any significantly exotic materials, lithium niobate tantalate or so, we can actually produce in our hands-on workshop in mid next year. We can actually produce resonators and we can characterize them. And I propose that as an exercise for people to sort of get somewhat more diverse training that combines clean room process and characterization techniques.
Yes. Okay, very good. I'm looking forward to have that hands-on training. That will be very interesting, very diverse, fabrication and measurement. So, okay, so If there is no more questions, I will stop here the session 1, and then we will continue at 11 with session 2. So if you have any questions regarding INFRACHIP or whatever, any other questions, please, I will stay here for the next 10 minutes. If not, see you everyone at 11 for the next session. Thank you very much.